Okay, so we're going to talk a little bit about how electrons affect each other around an atom. I think most of us are kind of used to thinking about an atom where we have something here in the center, and then we have our electrons on the outside of this. But we also remember we kind of make a distinction. We have two different levels of electrons. We have the inner part here, which we call the core electrons. And when we get to the outer part, we refer to these as the valence. So we want to think about these and how they affect each other and what consequences they have by being in a confined space with each other. So that's what we're going to see today. So what we need to talk about is the effective nuclear charge that we see on an electron. So for example, we know at the center of our nucleus, we have positive charges, and surrounding that, we have our electrons, which have negative charges. And so we want to understand, how does each electron actually, quote unquote, see that nucleus? How much charge do they actually feel? Well, let's think about two different positions. So for example, I've got this outer area of the electrons. These are maybe our valence electrons. And then we've got some of these on the inner part where you could think about the core of the electron. So what we should recognize is that these electrons that are here closer to the nucleus, they see all of this charge because they're right there by that nucleus. They can see it. But these now are kind of now shielding or hiding that nucleus away from the exterior electrons that are out here. So now, like if I think about this space in here, there are electrons in here that are blocking our outer electrons, our valence electrons, from seeing that nuclear core here. So that's what we mean by saying that there's an effective nuclear charge. This valence electron out here does not see all of the core because there are some electrons in between it, meaning between the valence and that nucleus. So it kind of cancels out some of the nuclear charge that it sees. So that's what we're going to be thinking about today, the effect of nuclear charge and something we'll call shielding. So to better understand this, we're going to look at the radial functions of our electrons. Remember, that tells us where we're most likely to find the electron. See, we have the 1s electron over here that's most likely found close to the nucleus. We have the 2p, which is found a little bit farther out, and the 2s that's even farther out. Now, when I say that, I'm saying that's the most likely position for them. But we recognize, for example, with the 2s, sometimes they can be found down here, which are closer to the nucleus. So we see what we call orbital penetration, where an electron from an outer orbital can sometimes be found closer to the nucleus than an inner electron from, say, this 1s orbital. So that's the concept that we're going to be thinking about here. This is the idea that we call penetration, again, saying that the 2s can and the 2p electrons can be found closer than the 1 electrons. Not always, but there is some probability of finding that. So that's the penetration, falling in down lower than where the 1s electrons can be. That's penetration. The concept of shielding is what we were just talking about on the previous slides, where we said, hey, most of the time, though, we see that this 1 electron is found between the 2s and 2p and that nucleus. So in other words, this 2s and this 2p out here, since they're farther out, these 1s electrons will shield us from seeing the full nuclear charge. That is what shielding does. We have a barrier because of these 1s electrons, the 2s, the 2p, they just can't feel that full charge. If we want to get a little bit more quantitative, we can actually apply some numbers to this. So we're going to define the effective nuclear charge as Z with a subscript EFF, so Z effective here. And this is just Z minus S, where when we're defining these things, we'd say that Z is our nuclear charge, or our atomic number, where S is how much shielding that we actually see on those electrons. So that's the concepts that we're going to be bringing forth to see how much a charge does an electron actually see? Now, Z is the easy one because it's just the atomic number of the system. So really what we need to determine is our shielding value here. So how we're going to do this is we're going to write out the full electron configuration according to principal quantum number. And we're going to separate groups of electrons. So here I've got just a generic sequence of our orbitals. We start with our 1s, 2s, 2p. We're going to group those together to show that, hey, they're similar electrons. Then we go up in our atomic numbers. We've got 3s, 3p. Normally in our electron configurations, we'd go to 4s, but we're going to keep all the principal quantum numbers together so that we can see all of them as a set here. So we're just going to rewrite the electron configuration in order of the principal quantum number, like we've got here. Now, the reason we're grouping these in such a way is that they all have different effects to the nuclear charge here. So if we're looking at just sp electrons, when we are looking at an np electron, meaning that we are in that quantum shell. So perhaps we're looking at an electron in the n equals 4 state. So I would be dealing with the n equal 4, so 4s and 4p here. Those electrons contribute to shielding by 0.35 apiece. Whereas if we go to lower shells, so now, for example, going down a shell to n equals 3, where I have the 3s and the 3p electrons, they are doing a better job of shielding because they're closer to the nucleus, so they get a 0.85. If we go down even further, n equals 2, where I've got now my 2s and my 2p's, now they contribute a full 1 to that shielding factor that we're going to get here. Don't worry, we're going to see an example of this here in a minute. D and F electrons are slightly different now. So if we're looking in a quantum shell, so if we're looking at electrons in the n equal 4, if I'm thinking about a 4d or 4f, whoops, not d, how about 4f, there we go. They again contribute only 0.35, where any lower groups will contribute as 1, so a 3d. Or I guess that's the only ones that I can have here. There's no 3F, there's no 2D. So that one in this case would be equal to 1 here, okay? So those are the rules that we're gonna have to do to assign what our shielding value actually is. All right, so let's do an example here. Let's look at vanadium, which has an atomic number of 23, and we want to find the effective nuclear charge for a 3d3 electron, okay? So first, let's just remind ourselves that we're dealing with the electron configuration of vanadium. So we've got an argon core, 4s2, and a 3d3 electron configuration. So that's what we're dealing with for vanadium, okay? And we specifically want to know what is the effective nuclear charge that's seen, for example, on this specific electron here, okay? So that's what we're doing here. All right, so according to our rules, we're going to write out our electron configuration out to the electrons we're interested in. So we're going up 1s, 2s, 2p, 3s, 3p, 3d. Note that the 4s electrons here are not part of this because they're farther out. They are in the n equal 4 shell, so they're farther away from the nucleus, so they don't contribute to the shielding here. As we start doing our counting here, we say, all right, we've got 1s, we've got 2s, 2p, we've got 3s, 3p. All these count for 1, so I've got a total of 18 electrons there that occupy those orbitals. So each one of them counts for 1. That's what I got there. And when I look at the shielding for the 3D, well, I've got 2 electrons outside that are going to shield this third electron. That third electron, we're looking for what's being affected by it, so we don't care about it here. We care about what's underneath it. Underneath it is those 2d electrons, and each one of them counts for 0.35. If I add that up, that tells me I have a total shielding factor of 18.7 from all of those electrons. So now I just have to put in my atomic number, 23, minus that 18.7, and I find out that a 3d3 electron has an effective nuclear charge of 4.3. So in other words, it's not seeing all 23 protons. On average, it's only feeling 4.3 of those charges. Now let's compare that to looking at the effective nuclear charge on the 4s1 electron. So now we're going to write out all of our groups again, where now we go all the way out to 4s. Now we're dealing with s electrons instead of over here we were thinking about d electrons. So now we have to think about a slightly different rule set and put it together in a slightly different way. So let's do that. First thing that we'll see here is we've got now our S for the 1s, 2s, and 2p. These all get 1, whereas the 4s only gets 0.35, and our 3s, 3p, and 3d are all now 1 lower, so they get that 0.85. Again, this is because we're dealing with the s electrons rather than the d electrons over here. So we put this all together. We come up with a shielding value of now 19.7. Still our same atomic number, minus now our new shielding. Now I get 3.3. So what we see here is a difference. That difference is important here, thinking about an effective nuclear charge on my d electrons of 4.3 versus that s electron is 3.3. Why is this, we might ask? Again, let's think about our core here. Here, let's draw my d electrons, and let's do green here. We'll do my s electrons out here. So the d electrons, they are shielded by whatever electrons are underneath them here. Maybe these are, the n equal 2 level down here electrons. They are shielding it from that full nuclear charge of 23. Hence we see some positive value, 4.3. But now when we go out to our s electrons, we have the d electrons that are also now shielding the s from that inner core. So we would expect to see a drop in that overall nuclear charge, and it drops by about 1. So that's how we can actually see this in practice. We see that each electron in here has a different amount of nuclear charge that it sees. Now, admittedly, the rules here are a little bit confusing. I definitely have to look at them a couple times before I say, oh, right, I'm dealing with d electrons, so I have to do this set of rules. I'm dealing with s electrons, so I have to deal with this set of rules. So there is a little bit to work on here, and we'll definitely go over this in class and do some practice on this because it does take a little bit of time. It's a weird thing that we're seeing here. But fundamentally, hopefully the physics that we're seeing here, this change of the effective nuclear charge that we just calculated here, hopefully we can see that now and we can understand why it actually exists. Okay? So that'll do that for effective nuclear charge that we're talking about today. Again, we'll talk about this more in class, but don't hesitate to reach out if there's anything I can help explain or clarify. And until I see you next, be excellent to each other.